Application of ultrasonic waves in the industries has been progressed considerably during the last 2 decades, especially in manufacturing processes. The effects are used to enhance a wide range of processes, such as machining, welding, metal forming, powder densification, cleaning, etc. And piezoelectric ceramics clearly have had the common use as a driving source of such waves. Sandwich ultrasonic transducers developed by Professor Langevin are vastly used by industries for high-power acoustic wave generation. In this type of transducer, piezoelectric rings are sandwiched between 2 metals and prepared for high-intensity vibration. As you can see in the picture, a central bolt also is required to mount and apply an amount of preload on piezoelectric ceramics. By considering the dynamic behavior, elastic damping, as well as inertia factors, finite element method is the most reliable way for analyzing the ultrasonic transducers. By employing finite element analysis, the resonance frequency of the transducer and different modal shapes could be seen and visualized under varying frequencies. In this video, you are going to learn how to use Abaqus to analyze a piezoelectric Langevin transducer and see different modal shapes of an ultrasonic transducer under varying frequencies. Although you can find a few videos with the same topic on YouTube, simulation of vibrating modal shapes of an ultrasonic transducer is very challenging by Abaqus. And in this video tutorial, we will analyze a different kind of ultrasonic transducer compared to the others. This is a diagram of an ultrasonic transducer with its dimensions. Based on what we already discussed, a typical ultrasonic transducer will be simulated and analyzed by Abaqus with specifications of 1 kilowatt power that will be released under electrical AC current, which has 20 kilohertz frequency and voltage of 1000 volts. That means its longitudinal vibration mode will occur when excited by 20 kilohertz electrical waves. Note that in this simulation we will not consider the effect of electrical potential and accordingly the amplitude of the vibration. It can be the subject for another tutorial video. Here at the bottom of the page is the reference that I used. So for additional information about how to design and analyze a typical Langevin transducer, you can refer to it. To start the simulation, first I open the Abaqus software. And I select explicit standard solver type. The first step in the simulation is to model every component of the piezoelectric transducer in the part module. And then in the property module we will assign material properties to each of them. So first I click on create part command. Then enter front mass in the name field. Then I select revolution from the type subsection under the base feature section and change the approximate size to 100 millimeters. And note that in the simulation I insert the units in metrics. Now that I have modeled the front mass, I will do a similar procedure for the back mass. Also, we repeat this procedure for modeling the pre-stressing bolt. Okay, here I should make an amendment. I will change the name of the first part. This is front mass, and this part that I inserted the name wrongly and not correctly, it is back mass, so I should rename it and change it to back mass. So this part here is the front mass. This is front mass. This is back mass. Now we should create the pre-stressing bolt. Okay, in case of modeling the piezoelectric rings and electrodes in the create part command, under the base feature type, we use extrusion instead of revolution. So here I changed the name to Piezoelectric. Now in the edit base extrusion command, type 6 millimeters into the depth field. For the electrode, we assign 1/4 of 1 millimeter for the depth of extrusion. Now I go to the mesh module and check the color of each individual component. As you can see, the color of pre-stressing bolt indicates that we should mesh it again correctly. So it should be partitioned. So I go to the part menu, then I choose partition cell extrude sweep. Then I select a closed edge under the bolt's head. I specify a direction. Okay. Again, from the partition cell, define cutting plane. I will define a plane with 3 points to partition the bolt. I will do it 2 times. Okay, back in the mesh module, so you can see that the bolt is correctly partitioned so it can be meshed correctly. Now in the property step, we define each material's properties in a separate section. Then we assign each section to each of the corresponding parts. For this purpose, I click on Create Material command, change its name to Steel, under the General tab, Density, and I insert the density value as 7,860 kilogram per cubic meters. After that, under the Mechanical tab, Elasticity, Elastic, I will insert the Young modulus of steel, also the Poisson ratio. Okay. To define aluminium, copper, and piezoelectric properties, we will do the same procedure with the corresponding values. To define piezoelectric material properties, in addition to the elasticity and density, we should define dielectric as well as piezoelectric properties. So first I change the name to piezoelectric. Density, elasticity, under the electric magnetic I select dielectric. I change the type to orthotropic, and then I will type the dielectric properties into the three appearing fields of D11, D22, and D33. Consequently, in the piezoelectric section here, I insert 0 into all the empty fields except for E311, E322, and E333, into which I insert the corresponding values. And I press OK. Now we should assign the material properties that we have defined to each of the components. So we should assign them to components. For doing this, I click on Create Section command. In the name field, I type steel, solid, homogeneous. Continue. The material is steel. Okay. I repeat this procedure for aluminum 7075, copper, and piezoelectric material. Now, from the drop-down menu in front of the parts section, I choose front mass. Then I assign a steel section to it. I also repeat this procedure for back mass and other components and assign the corresponding materials to them. So, assign section. Done. Front mass aluminium. Okay. Its color changes when you assign the material. Now back mass. Steel. Okay. Electrode. Copper. Piezoelectric rings. Piezoelectric. Pre-stressing volt. Aluminium. After that, in the assembly section, I bring in all the parts. I will bring in all the parts into the assembly environment. for example back mass. Note that you should also select auto offset from other instances. So I selected back mass. Okay, back mass, apply. I need one back mass, 3 electrodes, 1 front mass, 2 piezoelectric rings, and a pre-stressing bolt. I use coaxial and face-to-face constraints. Note that in the face-to-face constraint, also in coaxial constraint, the arrows should be in the same direction. Now I will put each component into its correct place. Okay, note that you should do this constraint assigning very carefully, and if you notice I made a mistake, so now I should do it again because of the mistake that I have made. So I should again do the face-to-face constraint, the back side of the piezoelectric rings, also the front side or the lower side of the piezoelectric rings. The arrows should be in the same direction, okay? So there is another, I think. Let me give it. So coaxial, the face movable. This is movable. This is fixed. Arrows in the same direction. Okay, yes, now this is correct. Back mass, electrode, piezoelectric rings. Now another electrode. Okay. This face, this is the okay, correct. Correct. Okay. In this level, after positioning the components of the transducer, I should define two planes which I want to partition the pre-stressing bolt by. And later I will describe the reason behind it. So first I hide the piezoelectric and electrode rings. For doing this, under View menu, I select Assembly Display Options. Now I choose I click on Instance tab. I press Set All Off and just check the boxes of front mass, back mass, and pre-stressing bolt. Apply. Okay. The piezoelectric and electrode rings disappear. Now I should measure under the Tools menu, query for calculating the distance between the lower plane or lower section or lower surface of the back mass from the top surface of the bolt. In the query window, I click on distance. A point on a plane at the bottom of the back mass and a point on a plane at the top of the bolt. Okay, the distance along Y direction is 26 millimeters. Also, the distance between the top surface of the front mass and the top the top surface of the bolt. A point here and a point here. Yes, you can see that the distance is 38.75 millimeters. So I go back to part module. I will create two planes based on my measurements. I click on Create Datum Plane. Now I select the little arrow, offset from plane, enter value, flip. Okay, so the first value was this value, 26 millimeters. And the second one was 38 point was this value. So I should now I should partition the bolt by partition cell, define cutting plane. So I select the bolt. Maybe I should select another one. Yes, datum plane, partition with datum plane. This is my first datum plane. Yes, the pre-stressing bolt is partitioned. Another one, another datum plane. So now we go to step module, view, assembly display option, set all on, apply. Now we can see all of the components of the transducer. In the step module, we will define two steps, one for the pre-stressing or preloading, for applying pre-stress onto the piezoelectric rings by a pre-stressing bolt. Also another step, which is the modal analyzing step, by which we can see different modal shapes of the transducer under varying frequencies. For doing this, first I click on create a step, change the name to pre-stressing, static general, continue. Then I select the non-linear mode active, non-linear geometrical mode active, and under the incrementation tab I will leave this minimum value to the default, and I decrease the initial step size and also the maximum step size. Now okay. Another step, it is model analysis. I should select linear perturbation, frequency, continue. I enter 10,000 and 40,000 for minimum and maximum frequencies, which will be tested on the transducer to analyze the various model shapes. So 10,000, 40,000. Now okay. In the interaction module, I click on create interaction property, change the name to general contact, continue. Under mechanical tangential behavior, penalty, and I set the coefficient of friction to 0.5. Also mechanical normal behavior, hard contact, okay. Another property, frictionless, continue. Tangential, yes. Frictionless, normal behavior, and okay. Now we should exclude, this was the reason why we partitioned the pre-stressing bolt by two datum planes. We should exclude the inner surface of the back mass and the peripheral surface of the bolt from the general contact, and the friction between the peripheral surface of the bolt and the inner surface of the back mass, there is no friction between them. So I insert the frictionless property because I want to define no friction between the pre-stressing bolt and the inner surface of the back mass. Also, we should define a tie constraint between the inner surface of the front mass and the peripheral surface of the bolt. So this is the reason that I partitioned the pre-stressing bolt. And so for doing this in the assembly module, I come back here to the assembly module, first I should hide the components that I don't need them. Set all off, just back mass and front mass. Tools, Manager, create the inner surface of the back mass. Excuse me. This is the inner surface of the back mass. Also the inner surface of the front mass. Done. Now I will bring in pre-stressing bolt, apply, bolt back is the peripheral surface of the bolt under the head of the bolt, between the plane at the bottom of the head of the bolt and the upper datum plane. So continue. For selecting correctly here, I select the selection type that selects from just exterior surfaces, that if there is an internal surface into the bolt, by picking this mode, those internal surfaces will not be selected. So here for back bolt, I will select each surfaces individually by holding down the shift key. 1, 2, 3, and 4. Another surface, bolt front, continue, 1, holding down the shift key, 2, 3 and 4. I will bring in all the components back in the interaction module. I click on create interaction. Change the step field to initial, general contact, continue. So as I mentioned earlier, we should exclude the inner surface of the front mass and corresponding peripheral surface of the bolt that is engaged with front mass, because we want to assign tie constraint between these surface pair. So I click on edit, I click front and bolt front, click on double arrows and OK. Also I told you that I want to assign no friction between the peripheral surface of the bolt that is engaged with the inner surface of the back mass. So here in front of individual property assignment, I select bolt back, also back, and frictionless. Click on 3 arrows and OK. So this way, the friction between the inner surface of the back mass, also peripheral surface of the bolt that is engaged with this part, there is no friction between them. Also, the inner surface of the front mass and peripheral surface of the bolt that is engaged with front mass, they are excluded from the general contact because we want to assign a tie constraint to them. Okay, here the general contact that I defined earlier is the global property. Okay. Also create constraint. I should define a tie constraint. Surfaces here. I want to highlight the inner surface of the front mass and the peripheral surface of the bolt. The master surface assignment is also correct. The master surface is the inner surface of the front mass, and the slip surface is the peripheral surface of the bolt, and finally, OK. Now I go to load module. In the load module, we should apply the pre-stressing load and the electric potential onto the piezoelectric rings. So here first I will hide all the parts except the pre-stressing bolts. Now I select remove faces, then I change the orientation of the view so I can see the pre-stressing bolt this way. I press on create load. Pre-stressing step. I select pressure, continue. So in order to apply the pressure, I should define a surface. Now, because of that, I change the, so selecting viewport, I change the surface selection mode to select from interior entities. Okay, before that, as I mentioned earlier, I forgot to all entities, yes. So if I select all entities, which is active now, when you select a portion of a space, all the faces, both interior and exterior surfaces, will be selected and will be disappeared. So here I have these internal faces. So I will change this mode to select from interior entities because we want to apply the pressure onto the interior faces. By holding down the shift key, I select these faces. Done. Well, I did a mistake, so YZ file, remove faces, all entities, Done. So I forgot to press the red cross. Now again here again I change it to select from interior entities. These 4 pieces should be selected. Done. And I select the brown color. I insert the value of 29,600 Newton corresponding to 34 megapascal. I want to insert this pressure onto the piezoelectric rings. And finally I press OK. So this way we apply the pressure. Now for applying the potential, electric potential, I will bring up the assembly display options, set all off, and just one of the piezoelectric rings. Create boundary condition, electrical magnetic, electrical potential, set 1, well, I think yes, this is very important that you assign the surface selection mode from exterior entities, so we can select the lateral side or the lateral surface and magnitude 0. Again on that side, zero potential, and the magnitude is 0. As I mentioned earlier, we don't want to see the effect of electrical potential, just we want to excite our piezoelectric rings. So apply the other ring, continue, zero. Okay, so let me correct them. I will delete them because I want to apply the potential from the initial step. This was the matter that I was forgotten, so I forgot to apply the potential from the first step, which is the initial step. So I will select initial, sets, maybe I should bring in the other piezoelectric. So this was the set 1. When you want to do this boundary condition, notice that in front of the step field select the initial step. Now because I have already defined the set, this is pre-selected here, so I just select the set 1 and the magnitude is automatically 0. Again, create boundary condition, step initial, electric potential, continue, set 2, okay, the other piezoelectric ring, set 3. Okay. After that, in the mesh module, first I convert all the existing parts to independent. Here I select them under the assembly tree and I will make them independent. I click on set part instance. I will select the whole assembly, done, and approximate global size will be changed to 2 millimeters. This is the size of the seeds of the mesh that we want to use in this simulation. Again, I will use this window. I will hide 2 piezoelectric rings, assign element type. I will select all the assembly except 2 piezoelectric rings. Note that we should uncheck the reduced integration here. Okay. Now set all off, just 2 piezoelectric rings. I will select them. The type of mesh is piezoelectric and the reduce integration box should be unchecked. Again, I bring in all the components. And finally, under the mesh menu, I again select all the components and I will mesh them. So finally, in the job module, I click on create a job, continue. So you can do some parallelization, because I have 4 processors in my computer. I can select 4, so this will increase the speed of your simulation, and I press on OK. So here, and I should now check to see if there is a problem in my simulation, so I click on data check. Okay, good. Okay, so a problem happened. What I forgot to mention is that for assigning the piezoelectric property, we should also specify a direction for it. So in the property module, I go to piezoelectric ring section. Now I should define a datum coordinate system. This is axis, this is for defining datum coordinate system. I want it to be rectangular. This is the origin of it, a point on x-axis, a point on y-axis. This is my datum coordinate axis, and now here I will click on assign material orientation. So because I have already defined a set, I will select it. I will also select my datum coordinate system, and the pre-selecting adjustments is okay, so I will press on OK. Now I go back to job module and I will check it again. As you can see, there is no problem. It's because this job is very time consuming. I have already done this job. Now I select my previous job and click on results to see the results of the simulation. First I select a proper view. Also I change the screen visualization to parallel. I will define a cutting plane, and this plane is the plane which is normal to the x-axis. This is YZ plane, as you can see, and also I will select the deformed mode. I also will bring in the frame selector. Okay, now we want to monitor the stress, or maybe strain or plastic strain in the first step, in the pre-stressing step, and we want to monitor the values in our model. So I go forward to see the stress, and you see as the time increments, which is the whole time for the first step was 1 second, and going in front of the time, you see that these stresses are increasing. If you want to see the deformation more obviously and also more exaggerated, you can select common option, common options, common plot options. In the deformation scale factor section, enter uniform, and you can increase it. For example, here I enter 100. Apply. Now you can see the deformation more obviously and also exaggerated throughout the transducer. This is our first step of simulation, which was pre-stressing a specified pressure onto the piezoelectric rings by the central bolt. Now to see the different modal shapes of the transducer under varying frequencies, here I will close the view cut manager. Also I will change to the undeformed shape. Here is the frame selector. Under the result menu I select step frame. Also I select this model analysis step, and these are the frequencies which are resonance frequencies. So you can see the different modal shapes of this transducer under these frequencies. So here I click on the first one, apply and animate. Okay, so we should decrease this scale value. Now apply. So you can see there are different modes: bending, torsional, and also longitudinal. You see that vibration frequency in this mode is about 19,400 Hertz. It was supposed to be 20 kilohertz, but there is a little difference with the expected value. And as you can see, the minimum amplitude is somewhere between the piezoelectric rings here. This is minimum, is nearly zero, and the maximum amplitude is on the front of the front mass and also back of the back mass. Also you can go forward and see other modes and their shapes. And you can see that the range of frequencies is between 10 kilohertz to 30 kilohertz. So thanks for your attention. If you have any question or comment about this tutorial video, please leave them in the comment section and hit the like and subscribe buttons to see more relating videos. Thank you.